All right, we'll give it about another minute or so just to make sure everyone gets in. All right, well, let's go ahead and get started. Welcome to the Circular Bioeconomy Systems Institute Member Hour Series. I am Alicia Moonbach, your host for today's session. The Circular Bioeconomy Systems Institute, or CBSI, aims to transform the traditional take, make, use, dispose linear economy system into a more sustainable circular bioeconomy system that regenerates natural resources, reduces waste, and minimizes environmental impact. In this next installment of the CBSI Member Hour series, we have Dr. Anurag Mandalika from the Center for Energy Studies at Louisiana State University joining us to discuss the role biomass residues from agricultural and forestry waste can play in enabling energy and industrial decarbonization, and particularly in Louisiana, where both energy and chemical production is a significant component of the local economy. Before we kick things off, let's get some announcements out and quickly go over some session ground rules. First and foremost, we are excited to announce the official launch of the CBSI website, where you can connect with other stakeholders and access resources of CBSI. You can find recordings of previous webinars, upcoming events, and publications related to circular bioeconomy systems here too. You can check out the website at cbsi-asabe.org. And I'll also drop that link in addition to a link for the 2024 CBS Day event held on July 28th in Anaheim, California, and the CBSI LinkedIn page into the chat. And for our session ground rules, first of all, please keep your audio muted during the presentation. If you have any questions, feel free to drop them into the chat. We'll also open for verbal questions during the Q&A segment later in the session. And finally, this meeting is being recorded and will be available for later viewing on the ASABE and CBSI websites. Now, without further ado, let's introduce our speaker, Dr. Anurag Mandalika. Dr. Mandalika is an assistant professor of research at the Center for Energy Studies at Louisiana State University. His research interests include biomass and bioenergy, biofuels, waste reduction and valorization, emissions measurement, carbon removal, ethics, and environmental justice. Dr. Mandalika holds a BS in Biosystems Engineering from Clemson University with a minor in Environmental Engineering, and MS and PhD degrees in Biological Systems Engineering with a minor in Chemistry from the University of Wisconsin-Madison. So I'm curious to learn more about some of these exciting opportunities to help transition the energy and chemical production industries from my home state of Louisiana toward more circular decarbonization practices, and I hope you are too. So please join me in welcoming Dr. Anurag Mandalika.
Thank you so much for the introduction, Alicia. I hope everyone can hear me okay.
Sounds good.
As Alicia mentioned, I'm an assistant professor of research at the Center for Energy Studies at LSU. A little bit about our center. We are mandated by the state to work on energy issues that are relevant and pertinent to the state of Louisiana, particularly those that impact the economy, environment, and citizenry. So I want to thank the CBSI and the ASABE for letting me share a little bit about the kind of work that's going on in Louisiana today, some of the unique challenges we face, and how the bioeconomy might be a concept that would be super relevant in this place and region. So for the member hour, I would like to cover a few different topics, maybe starting by establishing what we understand the bioeconomy to be, and taking a dive into Louisiana. I want to touch on two different topics they may not be apparent right away how they're related, but they are. And those would be the issue of energy accessibility and that of industrial decarbonization, and talk about how biomass might fit into that picture, what we currently do with biomass, production of fuels and energy, and I want to touch base on hydrogen a little bit, and then bring it all together with a discussion of environmental justice, not very in-depth necessarily, because I'm really not qualified to do that, but I do want to acknowledge its importance, and then come back to the concept of the bioeconomy. So I've seen a few different definitions and conceptualizations of what this term means. I found this from the White House. It's an executive order from the current administration. And basically, the policy statement is to advance biotechnology and biomanufacturing towards finding innovative solutions in a few different areas. And for us, primarily as ag and biological engineers and any other professionals present here, I welcome you, number one. But the things that are most relevant to us probably are those of energy, agriculture, and climate change. And then I did a bit more digging on the internet, and I found this wonderful infographic from the Wisconsin Energy Institute. And I felt that it does a really good job of giving a high-level introduction to the bioeconomy and what it might look like. So what I gather from something like this is that we're trying to make our current economy more resilient and sustainable for producing all the products that we currently do produce, which are on the right side of this infographic. And understanding that we're currently reliant a lot on petrochemical inputs, and finding a different source of inputs and raw materials that are more from renewables, biomass, and waste from forestry and agricultural industries, and trying to integrate that all into making our economy a bit more sustainable. The second reason I like this graphic is because it's from my grad school alma mater, so on Wisconsin. Okay, I will move on to Louisiana and go to the first topic, which I want to introduce, is that of energy accessibility. So I'm hoping some of you know Louisiana is a coastal state. This is where we're positioned in the map down here. And we are somewhat uniquely impacted, along with other states in the Gulf Coast, with being hit by hurricanes and tropical storms and having energy-related issues as a result. So I want to introduce this tool from the White House. It's the Climate and Economic Justice Screening Tool. And we will touch upon this later on in the presentation, but I do want to put a pin on it here. But we can use this tool and go to the different census tracts that are located on the coast. So of the 17 different census tracts, we've identified that 15 are defined as being overburdened and underserved. Among the various categories, which again we'll come to in a second, or almost an hour, climate change impacts all of them, especially being on the coast. We have an issue of coastal erosion and land loss as a result, and obviously being battered again by hurricanes and storms. And that is reflected as a lack of access to affordable energy, which 4 different tracts have been identified as having being affected by it. So the question here then becomes like, okay, what do you do in this situation when you do have a storm that impacts your community, and then you do not have access to power for an extended period of time, and maybe you're resorting to relying on something like a diesel generator to power through until power gets restored. And talking about restoration of power, the literature has identified some clear distinctions between rural regions and urban regions. Obviously, the recovery time is a lot faster if you're in an urban area compared to a rural area. So to give a quick example of a recent situation, so 2021, so about 3 years ago, there were 30 total fatalities after Hurricane Ida hit Louisiana. And it was identified that power outages were one of the main causes, if not the main cause of death after the storm. So it wasn't really necessarily the wind or the flooding, but it was the lack of access to power, especially as the temperatures were really high and people didn't have air conditioning, or people reliant on medical devices to help them through, and you didn't really have that. And just to compare to that of Katrina, the grid was incredibly more affected. In New Orleans, we found that they lost about 8 transmission lines and over 30,000 utility poles, which is twice as many that they lost during Katrina. So to try and combat that, I love this example. It was very recent in 2023. A community lighthouse was inaugurated in a town called LaPlace, Louisiana, just outside of New Orleans. And it's really a grassroots effort led by the community, represented by an organization called Together Louisiana. And they raised money, and then they went to the Department of Energy. You can see in the bottom photo here, the Energy Secretary Granholm inaugurating the facility. And the image on the top shows the conceptual idea of what this looks like. Basically, a solar power battery back array serving as a place where you can go and charge your phones or medical devices after you've been hit by a storm and you do not have power. So here I want to sort of introduce the first facet to this presentation is, can the bioeconomy concept let us plan similar models, right? And then moving on to the second topic I wanted to focus on regarding industry. So I don't know how many of you know, but Louisiana has a big industrial base. If you look at our statewide per capita energy consumption, Louisiana ranks second, just behind Alaska. So Alaska is super cold and dark sometimes. In Louisiana, it's pretty hot. So are we all just cranking up our air conditioning to no end? Well, it turns out that our industrial sector consumes a lot of energy compared to the national average. So the two charts on this slide, the one on the left shows you the US consumption by end use sector. So we have 4 different sectors: residential, commercial, industrial, and transportation. Industrial use is about 34%. And these are 2021 statistics. When you look at Louisiana in comparison, it's about twice that, or more than twice that. And it turns out that we do have a lot of oil and petrochemical production and refining. We have chemical manufacture, particularly ammonia. We actually have the largest production complex in the entire world in Louisiana. So this is a large consumer of energy. And this is also reflected in our emissions profile that we can see on this chart. So on the top, as the emission profile by sector for the United States, and on the bottom, Louisiana. If you look at the United States as a whole, transportation is the dominant consumer. Contrasting that with Louisiana, we see that industry actually emits a lot of greenhouse gases in this case, so over 60%. So with a lot of the recent federal initiatives on industrial decarbonization, there is a big push to work in this area. And this is the second part where I want to say, hey, are these concepts of the bioeconomy that we're all here to talk about, can they be a part of the wide array of solutions we have for this particular challenge? So if we talk about the bioeconomy, we have to talk about biomass. And I want to focus on residues a bit more in particular. But I think a lot of us might be familiar with the billion-ton study. It was first published in 2005, and one of its principal findings was that there is 1 billion dry tons of biomass that can be sustainably harvested in the United States each year. It's been updated a few times since then. The most recent one, the BT23 study, came out earlier this year, and the figures have been updated to show that there's between 1.1 to 1.5 billion tons of biomass. You can go on the website and look at the spatial distribution of where these are located. So if you are to go in and say, I want to build a biorefinery and convert and produce a type of fuel or chemical, you can kind of pick out which area makes the most sense based on a data set such as this. The other key finding from the latest report is that bioenergy can account for about 15% of future energy needs. I think that's 2050. Currently, it's about 5% in the United States. If we zoom into Louisiana, and this is just a graphic showing our forestry residues and agricultural residues or crop residues. So these include stuff like waste from thinning, sawdust, residues from lumbering operations. Ag residues include sugarcane bagasse. They include rice husks and corn stover. And this is the table No one likes looking at tables, but we do have some statistics on national versus Louisiana, and some other residues we have that we rope into biomass include fats, oils, and greases, municipal solid waste, and solids from wastewater treatment. So focusing a little bit more on Louisiana perspective, we know that storage of biomass can have a big impact on what kind of emissions come from it. There have been a few studies in a forestry context and also in an ag context, just with piling residues and then looking at the emissions that come off of them. In Louisiana, especially in South Louisiana, the only sort of topography you have are these large piles of sugarcane bagasse. So sugarcane bagasse, or SCB is the acronym I'll be using for this presentation, is the leftover fiber after you've extracted sugar from the sugarcane. So for the longest time, there just hasn't been an economically feasible way of utilizing this material, although that might be about to change rather soon. So these can be a source of emissions. Is there anything else that we can do with just residues in general from biomass processing? So one of the obvious answers is turning them into energy or fuels and using them as a source of energy. If you look at the current portfolio in Louisiana, the goal is from going to biomass and producing a bunch of fuels. We produce 4 primary types of fuels in the state, or biofuels in the state. 2 of them are alternatives to petrochemical diesel, biodiesel and renewable diesel. I think most all of us are familiar with what biodiesel is. Transesterification of fatty acid-rich sources produce a fuel that can be blended in with conventional diesel and run in a diesel engine. Renewable diesel is slightly different. It's produced in a very different way. And the attractiveness behind this is that you do not have to blend it. You can run it straight in a diesel compression engine. We also produce densified biomass fuel, or DBF. It's a more technical term for wood pellets, is how most of us understand it. And then we do have a little bit of RNG, or landfill gas, that's produced from capturing the methane off of landfills. I want to focus on renewable diesel a little bit more, just because it is a pretty big source of energy. So the US actually produces quite a bit of it, over 3,000 million gallons per year is the capacity. It's produced in 11 different states, as this graphic shows where the production is coming from. And it turns out that we produce about 40% in Louisiana of this material. So there's a distribution network for how all the wastes and greases come into the state, and then they're transformed here in 3 different refineries. And then, as far as I know, none of that fuel is actually used in state. We export it to states where there's better incentives, such as California, for example. We also import a bunch of renewable diesel, which shows you that there is clearly a demand for this fuel. And then the second type of fuel that I did want to talk about is DBF, or wood pellets. It includes more than that. It can also include briquettes or logs. The idea here is that sawdust or wood residues are not really very dense. So if you want to ship them across long distances, which we currently do, you want to densify them and make it more economical to ship. So the chart here is a Sankey chart. Basically, it's showing you stream flows between different groups or entities. So from left to right, it's going from different states to territories to different countries. So I produced this to show, the thickness of each stream indicates the quantity. Our current capacity in the United States is about 12.7 million tons per year. And then forests of the South contribute over 80%. The rest of it comes from forests out west of Washington and Oregon. As you can follow the stream flow to the right, most of this material is actually exported, over 85%, primarily going to the UK for their energy production, and then countries in the EU and Asia. We do use a little bit of it domestically, but I think these are more heating grade pellets, not necessarily utility grade pellets. And Louisiana accounts for about 10% of our total DBF capacity. And to put all of that into context, this donut chart shows total primary energy generated in Louisiana in 2021. So primary energy is just energy that's taken out from the ground or biomass or biofuels before you convert it to something else like electricity. So it's clearly highly dominated by by natural gas and some other fossil fuels. And then biomass and biofuels account for about 5% currently of that primary energy capacity. And this is the breakdown, most of it coming from renewable diesel, a little bit from biodiesel and densified biomass fuel, and a very small amount from landfill gas. That said, I mentioned earlier that there is some interest in utilizing more biomass as we move forward. So there have been several projects announced, again, spurred by investments by the federal government in this area and into advanced biofuels, primarily SAF, or Sustainable Aviation Fuel, and Sustainable Maritime Fuel, or SMF. So these have been announced to go into effect potentially in 2 to 5 years. And if all of these plants go into production, we're looking at a displacement of about 8.5% of total energy produced in Louisiana using biomass-based fuels. Most of it is driven by an interest in SAF with a desire to decarbonize the aviation sector, a little bit also from sustainable maritime fuel. We're producing a different type of DBF, which using sugarcane bagasse that I did want to mention because we talked about bagasse a second ago. And the concept is similar. They want to produce pellets from the bagasse and then ship it overseas, primarily to the UK for energy production there. So I did want to talk a little bit more about hydrogen because it's somewhat interesting in this context of fuels and chemicals. This comes from the Department of Energy's H2 at Scale initiative, and basically looking at different applications. Most of us are familiar that it can be a really good transportation fuel because the byproduct is water. So beyond just producing electricity or used as a fuel, there's some other applications which are somewhat more relevant when it comes to Louisiana, particularly producing ammonia or fertilizers and use another as a feedstock in other chemical industry. So hydrogen is a colorless gas, but we've decided that we want to give it some colors to identify how it's made and where it's coming from. And so this is, some of you might have seen it, it's the hydrogen color spectrum or the color wheel. We do produce a lot of hydrogen currently, about 10 million metric tons per year. And the majority of it comes from the steam reforming of natural gas. And we call it as gray hydrogen towards the right of here, shown as originating from fossil fuels. It has the lowest cost of production, a very high technological readiness level, or TRL. And then there's a few other things that are more interesting. Using renewable energy and hydrolysis, we refer to as green hydrogen. And if you take that same hydrogen you produce from natural gas, but include carbon capture, then you can refer to as blue hydrogen. And there's a few other different techniques. What's interesting is that we don't see a color ascribed to bio-based hydrogen production, which I'll come to in a second. But I did want to point out that the Department of Energy has a hydrogen shot goal, which is referred to as 111, or bringing the cost of hydrogen down to 1 kilogram per ton $1 per kilogram in 1 decade. So we've been trying to compile what that looks like, comparing the emissions and the costs associated with each type of hydrogen production. And this is not an exhaustive list, but we wanted to include gray, blue, and green hydrogen. The emissions are in blue on a kilogram of CO2 equivalent per kilogram of hydrogen produced, and then the cost in dollar per kilogram of hydrogen. So gray hydrogen, lowest cost and some of the highest emissions, and then blue and green hydrogen. Blue, again, is when you capture the CO2 from gray hydrogen and sequester it. Obviously, the costs go up because of the added steps, and then green hydrogen using electrolysis from renewable energy. And then we included DF refers to dark fermentation. It's a fermentation pathway, primarily bacterial, that can produce hydrogen by consuming carbohydrates or lignocellulose. And there's a few different emissions factors associated with them. The data is a little sparse when it comes to the cost, but then going back to the goal of the hydrogen shot, these are potential areas where we could try to do the research and bring the costs down associated with them. A particularly interesting one is the last column, which is AD plus SMR. So it combines two different techniques. AD is anaerobic digestion, and SMR is steam methane reforming. So by themselves, they have very high TRL because we know how to do that, and we've been doing it forever. So combining them and actually producing hydrogen through anaerobic digestion, also it was assessed in the literature that it's not a super emission intensive process, and the costs are fairly competitive. So that's another attractive option. So together we pulled them into this concept called biohydrogen. So basically produced from biomass, again, which we don't currently have a color ascribed to yet. So I want to introduce this case study. So basically a back of the envelope calculation. So Louisiana has several attractive features. We have the Mississippi River flowing through the state, which is a huge way for a lot of industrial traffic to move through, including biomass, grain, etc. So we conceptualized an idea and we're like, hey, can you produce hydrogen in a hub, biohydrogen in a hub, and use that as a way to decarbonize ammonia production in this plant all the way to the southeast, near New Orleans. So the other advantage is that we do have a hydrogen pipeline that connects Texas and Louisiana, and it does pass through Baton Rouge up here through New Orleans. So if you were to produce hydrogen somewhere along the path of the pipeline, you could easily ship it through here. And then in this particular example, we're considering that there's 4 different raw sugar factories. They generate bagasse on site. It could be either trucked in or barged down the river to this facility where you use a technology to produce hydrogen and then you ship it by pipeline and help this facility decarbonize. So what that looks like in a bit more detail, again, the goal being decarbonizing ammonia production or reducing emissions. So that particular facility was producing around 720,000 metric tons of emissions that you can ascribe to ammonia production. And in our case study example, if you took all the sugarcane bagasse from those 4 different factories and digested it anaerobically, and I found some data from literature for conversion factors and such. Obviously, you produce biogas, you also produce a digestate that could be sequestered by using as a fertilizer. And then separate out the CO2 in this stage using some kind of separation. Membrane separations have some potential. And then get the methane out and then transform it into hydrogen and clean it in this process. And again, capture the CO2 coming from here and sequester all of that carbon. A lot of moving parts, I know, but this is basically the overall schematic. We estimate that you can sequester about 950,000 metric tons of CO2 using a process such as this. Obviously, we haven't done any of the cost analysis, so I don't know how expensive this would be, but this is a conceptual design of can you decarbonize an ammonia production plant. So basically, if this worked out as intended, this could be a carbon negative process for producing ammonia at this one facility. So putting a few of these ideas together, at the center would be a facility that would produce biohydrogen using ag residues or forest residues and some other fat, oil, and grease-rich residues, such as seafood processing. Again, these are all co-located almost near the coast. And most of the time, you would produce hydrogen and try to assist in, a decarbonized chemical manufacturing pathway. And then the way we would tie it to energy resiliency is when there is a tropical storm or hurricane, you lose power. you could combust that hydrogen and generate electricity for that brief period when that is gone. So again, I haven't done the economics, but this could be sustained in a way that you're producing high quality hydrogen gas to be used in chemical manufacturing context, and producing an electricity when you need it. So we're tying the two principles of industrial decarbonization and improving the energy resiliency of the Louisiana coastline. And that brings us neatly onto this concept of environmental justice. So I remember saying, or if you remember me saying, to remember the CEJST tool, the Climate and Economic Justice Screening Tool. This is a result of an executive order issued by the current administration within the first week of taking office. But basically, they have identified census tracts depending on how they've assessed 8 different factors, including climate change and energy and pollution and some other issues. But you can use this tool to hover and click on a census tract and see what all the challenges that affect it are. And this is from a recent report that was published at our center, and the percentage of population identified a disadvantage in Louisiana puts us in number 6. So Oklahoma leads the country as the population that's most affected as disadvantaged. And we are at number 6. So a few more facts from that analysis is that nationally, if you look at the percentage of African Americans as a population, of about 14%, and the earnings are reflected at about 3/4. And then in Louisiana, that disparity becomes even more stark because they represent about 1/3 of the population, but their earnings are only 2/3 of the state average. So like one way of defining this economic disparity is to look at incomes, obviously, and the other way is pollution. If you look at this map, the blue are all the disadvantaged communities. We already talked about the coast that were part of this. Most of the chemical manufacturing plants and units are located along this stretch of the state, and these are clearly also identified as disadvantaged communities, right? So when we talk about environmental justice and we talk about bringing in the transition to a bioeconomy, how do we ensure that we are doing this in a way that makes the benefits more equitable and also reduces harms to the populations that are next to where some of these facilities might be going in? So if I sit in my office and design a bio H2 hub and I say, oh, I want to place it in a certain parish in Louisiana, but then there will be people that will be impacted by that. So I think it should be the focus of people working in this area to ensure that we don't repeat some of the mistakes we have done in the past. And we have some guidelines for how to work with this. Some of you might have heard about the Community Benefits Planning, the Justice 40 initiative, which basically says that 40% of the benefits accrued from any project need to go to the communities that will be impacted by it. And it also comes down to engagement, which is not a perfect word, but getting community input and understanding what their perceptions are and what they would like the benefits to look like. All that goes to show that we need to be working super collaboratively with other social scientists and folks in humanities who have been doing this kind of work for the longest time to understand and incorporate perceptions of the community and ensuring that they do receive the benefits and not just all the harms from any kind of development. So we did a little bit of this type of work in a slightly different context. We've been exposed to information on energy transition very recently, especially in Louisiana, given all our geological and natural resource benefits or attractiveness. So we did a study. We pulled students at the flagship school and said, hey, what do you guys understand about all the different terminology you're using? And we asked a few different questions, and this is a small snippet of that data set. And we wanted to see what sort of trust they had behind some of these terms. So we had 5 different commonly used acronyms and terms, including carbon capture storage, direct air capture, bioenergy, carbon neutral, and net zero. And I think most students indicated that their understanding was about moderate when it comes to most of these terms. It was a little low when it came to direct air capture. And then the trust was behind understanding, which sort of makes sense, right? Like, so is this a way for us to better know where the community stands? If you were to expand a survey like this to a large population, can you glean more insights on what people understand and where they see some of the gaps being? Again, this is, we need to do a lot more of this type of research and even better research, working with folks that have been doing this for a while. So coming back to the concept of the bioeconomy, going back to this infographic, the only thing I would like to add to this is including that community engagement piece. I think to ensure that we do this more equitably and sustainably, we would need to be talking to the folks that this would impact. And with that, I think I'm a little fast today. Thank you.
Well, thank you. That was an excellent presentation. In just a minute, we'll open up the floor to any questions or comments, or maybe give it a minute if anyone needs to type them into the chat. But I'll start off. Have you, I know you said you weren't really an expert in the hydrogen area, but since you gave the case study there, have you had any conversations or been in any discussions to kind of understand how receptive some of the maybe sugarcane producers or the seafood industry folks, how they might, how receptive they might be to some of these ideas of these kind of hub kind of facilities?
I think that's an excellent question. So while working for the last, I guess, 10 months in this role, I've noticed that we don't have the greatest communication between an established conventional energy sector and like the ag and forestry sectors. There's not really a lot of conversation going on. And we know that there's opportunities that lie in both of these areas. So one with the feedstock to decarbonize and one with the goal to decarbonize. So the short answer is no, because we're just not having these conversations at an in-depth level. There's not enough fora or media for this to happen. And hopefully that'll change as, you know, these conversations permeate different communities. Again, these are located sort of regionally too in slightly different areas. Some of it's more urban and techie and suits, and the others more blue collar and rural. So it's a challenge, and I think there's a lot of work for researchers in particular to do to initiate and engage in this conversation.
Thank you. What other questions do we have? Feel free to unmute yourself, type them into the chat.
Alicia, could I ask a question?
Absolutely, Jim, go ahead.
Yeah. First of all, I would want to make a comment. I mean, this was an excellent presentation, and it's the kind of things that we like to see in the Circular Bioeconomy Systems Institute that was just formed by ASABE. And I hope you're familiar with that. If you're not, I would encourage you to become more familiar with it. The new institute in ASABE, the Circular Bioeconomy Systems Institute, has what I think you suggested is needed, and that is opportunities for other disciplines to work together, particularly social scientists, but also other disciplines to bring the technologies and the understanding of adoption and acceptance and impacts are really important. But we have in CBSI, Circular Bioeconomy Systems Institute, an option for people to join in this, whether they're members of ASABE or not. We encourage ASABE members to be a part of this, and many of them already are. But we have what we call an affiliate CBSI membership, so that people from the outside can join in. And we already have economists, social scientists, and chemical engineers and agronomists and biologists joining in now to be a part of it. And of course, it's just starting, and so we still have a lot to do. But I would encourage you and others on this in this presentation to go to the website that Alicia mentioned earlier and take a look at some of the things that are just starting to happen because of some of the same things that you talked about. One of the things I wanted to ask you, though, is that you typically just talked about the bioeconomy as opposed to circular bioeconomy. And I wondered if you had a reason for doing that. And then your diagram that I really liked that you showed was on circular bioeconomy. And I'm just curious about your perspective on that. Thank you.
Yeah, first of all, I want to thank you for the recommendation. I've been a card-carrying ASAB member since 2009, so I would love to join
Excellent.
the CBSI. With regards to your question, I don't think I had a very strong reason for not mentioning circular. I guess I am poorly informed on the distinction between the two, if there is one. But if I did lapse on including the word circular, it's probably because I just forgot or I didn't think hard enough about that. But yes, I can't take any credit for the diagram. It comes from the person that made it. But I liked it because it gave me a high-level overview of the concept while letting me learn about it very quickly.
Okay, well, yeah, thank you. Well, a lot of people get confused if you don't use the word circular, indicating that we're already doing bioeconomy. We've been doing bioeconomy for a long time. What's different? And so that's why we like to include that. But anyway, thank you for your interest and your excellent presentation today.
And thank you for the suggestion.
And you'll find those links to the CBSI website and all of the ones that I mentioned earlier again in the chat. I just dropped them in again. Another question that popped up here, while removing biomass for energy production can provide immediate economic benefits, it also has cost associated with it. Biomass in agricultural fields, such as crop residues and cover crops, plays a crucial role in maintaining soil health and ecosystem stability. So removal also affects the environment. Is this considered in the biomass inventory? So we're looking at costs and we're looking at environmental impacts. Are those considered?
I think that is an excellent question. To my knowledge, the way the billion-ton study is done, they incorporate the ecological impacts of removing biomass. For example, corn stover, like you mentioned. I think they have factored that into their calculations. They do attribute that some of it must be left on the field for sure for the next planting cycle. The difference, I would say, between something like corn stover versus sugarcane bagasse is a lot of that material is already concentrated in one site when it comes to bagasse, because these are not field residues necessarily, these are factory or processing residues. So we're trying to make another distinction and go a little finer at the expense of losing more material, but we're saying this is all in one site. So that reduces your cost a little bit, but obviously there is absolutely a cost associated with it. Just to give a bit more context, we've talked to some producers of bagasse or producers of sugar that also produce bagasse on the side. They estimate that doing nothing and storing it as a pile, they still have to manage the pile or else it could combust because of all the chemistry and microbiology going on. One of the producers we talked to said their costs are about $500,000 a year just to run large equipment and keep turning the pile over and making sure it doesn't catch on fire. So there are inherent costs maintaining that storage, and there are inherent costs to the environment. So the question becomes, and obviously this needs to be a more detailed analysis, and I'm sure someone's done it. But the question is, where do you balance that, and how do you promote a bioeconomy while ensuring that some of those costs and expenses are mitigated? Does that answer your question? Hopefully.
Yeah, that was my question, and thanks. That was a good answer. I'm glad that that was considered. I appreciate that the there's a cost in maintaining that biomass inventory, the fire protection measures. That's often the case. Wood chip piles, and all kinds of things at mills. So good point. Thanks for that consideration.
Thank you for the question.
All right, any other questions? We're happy to take them if you have them. Comments?
Yeah, this is Scott. Can I ask a question?
Absolutely, Scott, go ahead.
So I've heard a lot about turning biological material biomass into a product that can function like coal, bio-coal. Has there been any work on that? I know Canada banned coal. Well, the problem with that is you still need coal and coke to make steel. So they were pushing an ISO Technical Committee 238 for test standards for bio-coal, and that's just been intriguing to me.
That is a great question, and I know less than you do about biocoal. I am not familiar with that. So you're not referring to charcoal or biochar, correct?
No, they want to add to their scope and description of ISO Technical Committee 238, which is solid biofuels, pyrogenic biocarbon, which would be biochar, industrial biocarbon, and the biocoal. And it really came out of Canada because of the steel industry. And that was a discussion at their meeting last week in Europe. So
Yeah, thank you for mentioning that. I will have to read up on it. There's a new product, seems like every single day. But yeah, I appreciate the heads up.
I'll put something in the newsletter if it gets approved by the ISO Technical Management Board. It's just the committee believes this is what they should do, but we'll see.
Thank you.
Okay, great, thanks. Thanks, Tom, for your comment. Tom DeBrock enjoyed your presentation, and he also mentioned that he joined the LinkedIn group, so thank you for that. Any last thoughts or comments for our speaker today? Got a great presentation, lots of compliments. I'll just give it that Zoom minute just to make sure. All right. Well, again, let's thank our speaker for today. I want to thank you all for your participation. And I want to give a special thanks to our speaker, Dr. Anurag Mandalika, my co-moderator and ASABE Director of Membership, Sarah Rodriguez, and everyone else who contributed to making this member hour possible. If you have an idea for a topic or a speaker for another member hour, please reach out to any member of the CBSI leadership team. And remember that all sessions in this series will be available on YouTube via the ASABE and CBSI websites. If you're eager to join or to connect with others and advance the circular bioeconomy systems movement, mark your calendars for the 2024 CBS Day event in Anaheim, California on July 28th. Head to the CBSI website or ASABE's meeting registration page at asabemeetings.org for more details. And also follow the Circular Bioeconomy Systems Institute group on LinkedIn. And a link to that has been added to the chat. So once again, thank you all for being here and sharing your time with us today. And we are excited about hosting you again at future ASABE events. Thank you all. Have a great week.
Great job, Anurag. Good job.
Thank you very much.
Thank you.
Thanks for the opportunity. Have a good week. Bye.